So here's my sketch of the periodic table. Electron configurations. So in an atom, where are the protons? Protons, electrons, and neutrons. Where are the protons? In the nucleus. And where are the electrons? Outside, orbiting. So if I drew that, let's say I drew, so there's a proton, electron floating around out here. Right, that would be hydrogen. Let me write these numbers in. 1, helium is 2, lithium is 3, 4, 5. These are the atomic numbers. 10, 11, 18, 19. I didn't put all of those in. Chromium is 24, zinc is 30. Electron configurations are referring to a certain pattern that the electrons make when they go backwards. So let me draw this. So let's say that's a nucleus. In this first sphere I draw here, that's an orbital where electrons can be. And then if I drew another orbital where electrons can be, I did that. And I drew another one out here, so electrons can be in this orbital. And I did this. I went the distance from the nucleus to where this first orbital is. And then I can also draw up here, that's the distance up to the next orbital. And I draw another one, that's the distance up to the next orbital. And I drew it like this. I said, this is nucleus, distance from the nucleus is along this axis, and I went, okay, starting here, so there's one spot that I'm saying is this orbital. And then a little further out, there's another one. That's this distance to here. And then another one a little further out that would be up to here. This diagram, you see what I'm diagramming here? Distance to the nucleus. To do electron configurations is actually very easy. You start like this, without even looking at the periodic table. If it's an electron configuration problem, think like this. 1, 1, 3, 1, 3, 5. Meaning, go 1, 1, 3, 1, 3, 5. And if you keep them neat and symmetrical like that, I call this, what do I call it? The Christmas tree diagram is what I call this. Books have stopped doing this. I don't know why, but this makes it very simple. What these are those, so there's that first ring I had, that's this one. The next ring out is this one. The next ring out is this distance. So this is really distant from the nucleus. This third one out, so the first one, the second one, the third one. The third one out, there's like 3 places for electrons to be. But this is a repeating pattern. If you can do 1, 1, 3, 1, 3, 5, and then these that are single by themselves, those are called S. call those S. And you number them. This is the first S. 1S, 2S, 3S. The triple ones that are 3s, those are called p orbitals. So put p's there. SP goes SP, I think we use lowercase for these. I'll try to make these look like lowercase. So the single ones are S, the ones with 3 are the P's. D orbitals have 5, and there are F orbitals that have 7. So it's just like the odd numbers: 1, 1, 3, 1, 3, 5. This is what we would call the first shell, and it just has the S type. This is the second shell, it has the S type and the P type. So these are 2P. There is no such thing as a 1P. So if you can get this labeling down, this is very easy. Now we're in the third shell, and the third shell has S, P, and D type. These are the D type orbitals. So we started 3 here. So these are the 3 P's, and these are the 3 D's. You with me so far? So there is 1, 2, 3, 4, 5, 6 levels out. There's the D-type orbitals, and there's 5 places for electrons to be in. All right. I'll just sketch in that here. There's actually a 4S, 1S, 2S, 3S. Instead of putting the 4S up here, I'm just going to kind of stick it here, just so you know the pattern kind of breaks down a little bit. But let me just leave that there and say this. If I said, give me the electron configuration of carbon, if you could sketch this out, margin on a piece of paper or something, you would go, okay, carbon is 6. So if I'm doing carbon, and it's, that's not 6, it's 6. Okay, you do this pattern. You go 1, 2, that represents 2 electrons. Electrons have what we call spin, and the reason they can pair is it's like a magnet, north and south attracted to each other. You flip it, so north and south is attracting here, and south to north is attracting here. So when there's only one orbital, when you start counting, then I go to this next orbital. So I went 1, 2, 3, 4, and then when you get to orbitals that there's more than one, you put 1 in each, and then you go back and fill them up. So let me do that again. I would go, if the atomic number is 6, I would go 1, 2, 3, 4, 5, 6. This is one way to represent the electron. Oh, I did that wrong. 1, 2, 3, 4, 5, 6. That's one way to represent electron configurations in what I call the Christmas tree diagram. Here's another way to represent it, which is the way you're usually asked in tests. 1S, the 2 tells me there's 2 in there. Then 2S is next, the 2 tells me there's 2 in there. And then 2P, there's 2 electrons in there. That's another way to represent the electron. So you're looking at 2 different ways to represent the electron configuration of carbon. There's one. This is another way. Let me do, instead of carbon, let me do phosphorus, 15. So if I did 15, I would do it like this. You look at the periodic table, you look at phosphorus, you see the 15, and you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Drop that a little. 11, 12, 13, 14, 15. That's one way to represent the electron configuration of phosphorus. The other way is this way. This was carbon. If I did phosphorus, I do 1s, 2, 2s, 2. 2p is next, and there's 6 in that. 3s is next, and there's 2 in there. and then 3P, and there's 3 in there. So there's another way to represent the electron configuration phosphorus. You with me? Notice, first notice this. So if you can sketch this out with the S's and the P's and the numbering, I always tell you to just start with 1, 1, 3, 1, 3, 5, and then label things. But notice, if I took this helium from over here, so I sketched the periodic table here, just for today, I'm going to move it over here. It's over here because it actually matches the properties of the noble gases. But if I put it over here, notice what's going on. If I want the electron configuration of hydrogen, it's that. If I want the electron configuration of helium, it's 1, 2. So this is element number 2. And notice I was filling an S orbital. Well, let's say I continue, and I go, okay, I've done 1 and 2, let's do 3. Notice I'm filling an S orbital when I get to lithium, and I'm filling an S orbital when I get to beryllium. Now if we went to 5, we're filling up here. There's boron, there's carbon, that's nitrogen, that's oxygen, that's fluorine, and there's neon. So I was here. Now I'll go back over here for 11, and again I'm filling an S orbital. That's sodium, and there's magnesium. The point is, any of the atoms here, we call that the S block because that's when you're putting in electrons in one of the S's. So if you're here, and you're doing this configuration, you're in the S block, so you know that's where you're going to end. You're going to end in one of the S's. If I continued and I went over here, so I jump across the gap and I go to 13, now I'm here. So aluminum, silicon, shouldn't have left that there. Aluminum, silicon, phosphorus, sulfur, there's chlorine, argon. Okay. This is kind of where the pattern starts to break. But you remember I told you, let me move the d orbitals up a little so I can squeeze this in. D, these are 3. So I got to here, argon. So I'm going to go from 18 to 19. Notice I'm back in the S grouping here. That's why I told you there is an S here. That 1, 1, 3, 1, 3, 5 is a quick way to get some lines drawn on a piece of paper. But just remember the 4S starts here. So the 1S, we were in the first row. 2S, we were here in the second row. This is 3S. And notice once you finish the 3P, you come around here and you start with 4S. That's why the 4S actually goes right here. And then once you fill those two, you're in your 3D. So this is called the D block. This is, I didn't write all these in. We call this the S block, this the D block, and this is what do you think we call this block? Did you say P? You did, yeah. You're filling the P orbitals when you're doing this. So realize this pattern, the 1, the 1, 3, 1, 3, 5, I tell you to start with. You can actually get that by looking at the periodic table, which you always have one for the test. So 1, 1, 3, 1, 3, 5. The 4S does come next. So then you get the 3D, and this is that's the first row, second row, third row, fourth row. This is the 4P. So you've got the 3D and the 4P. So the 4P would go here. So here we are in the 4P, 36. If we go to 37, we're back to the S. So that would be S. And now we're on 1S, 2S, 3S, 4S. Now we're on 5S. The F orbitals, I never deal with these, but that's what this down here is. So the F orbitals would have 7 across. So if I were doing an F, I would have one more on either side to keep it symmetrical. You see what I'm saying? So that 1, 1, 3, 1, 3, 5 is just a quick way to get started. If you want to fill everything else up, put all the orbitals in where they go, you just follow the periodic table. You start with the 1s, you go to 2s, 2p, 3s, 3p, 4s, and yeah, it's 3d here. So here you're filling the 1s, here you're filling the 2s, here you're filling the 3s, here you're filling the 4s. But we're on row 4, but these are D, so the D's are like shifted down one. So this is 3D, and just below there will be 4D being filled up. You see this pattern in the periodic table? Okay, another thing to point out is the numbers tell you which shell you're in. So the first shell only has one suborbital, subshell. This makes up the second shell. Those and this make up the third shell. There's 4s and 4p. There's 4s, 4p, 4d, and 4f. You would actually get all the way to the s, this section down here. So this section down here. But the pattern, what I'm getting at is, the first shell has only S. The second shell has S and P. The third shell has S, P, and D. The fourth shell has S, P, D, and F. The fifth shell has S, P, D, F. And yeah, there would be one more, and it would be 9. This was 5. D is 5, so it would be 9. But really, we don't get that far. By the time we get past the 2 F orbitals, or to the bottom of the periodic table, they don't go anymore. But just so you see this pattern, the first shell has only S, the second shell has S and P. The third shell has S, P, and D up here. The fourth shell, this is where they start to mix, but there's 4S, there's 4P, and yes, 5S starts next, but you get the 4D next. So if you're looking at the periodic table and going across, you would be on 4D next. So you can get the full pattern of how these line up, but still there's only 1 for the first shell, there's these 2 for the second shell, there's 3 in the third shell. When you get to the fourth shell, you have S, P, D, and you'll have an F if we kept going up. You with me so far? So here's one way. Which one was that? Oh, okay. Yeah, let me say this now. When you fill the S's and the P's, that's when you're all the way over here. This is starting here. You've got the 2S and the 2P. When you have the 2S and the 2P full, and then nothing above it, those are all empty. That's when you're on the noble gases. If I continued with this and I went, now the 3S and the 3Ps are full, now I'm here. I'm over, when the S's and the P's are full, you're at one of the noble gases. I can fill this S and this P, but I would go, then I would go across the transition metals. 1, 2, 3, 4, 5. Kept going across the transition metals. Now I'm at the 1, 2, 3. Now I'm filling these. There. Now I'm over here at red color. When it's the S and the P's are full, that's the noble gas configuration. You with me? Having said that, and the one exception though, is since we put helium over here, when you have so just those two electrons in the S, that's helium. If you continue to fill and you get these full, then you've got to neon. And then when you get to this S and P, then you've got to argon. And then if you fill all the way up to the 4P's full and nothing above, then you've gotten over to krypton and continue like that. So the S and the P's is a special configuration. We call it something else to point out, just because we're here. Do this. That with 4 electrons is beryllium. If you have a shell and then you have the next shell up, actually, I think this will go better if I go on up to that with these full. If I ask you what is the charge on a magnesium ion, what would you tell me? +2. Electrons are negative. So notice we've got this shell and then we've got this shell full. Beryllium has a tendency to lose those 2 electrons. Electrons are negative. That's how it ends up being 2+. And notice once you remove those, you have the noble gas configuration. That's why it stops there. That's why, I mean, you might ask yourself, there's beryllium. Why isn't there such thing as a +1 beryllium? It just loses 1 electron. The reason it's able to exist but still have a charge, because you would think the charges would want to gain those 2 electrons and be neutral. The reason it can exist like that is because the noble gas configuration has this special stability for it. And it's the same idea if I had, instead of beryllium, if I had lithium. No, now I'm talking about sodium. If I had sodium, it will lose 1 electron, and now the 3 level is empty, and we're just at the 2 level. That's why it only loses that 1 electron. It's nice and stable like this. The flip side is, once you start filling the p orbitals, that's really too many electrons to lose. I mean, you lose 1 electron, you're already a positive charge. And you're trying to get a negative charge to leave that positive charge. But once you have too many, now this can achieve, where are we, 3s, I guess I'm here. 1, 2, 3, no, I'm on silicon. So that would be silicon 2, 4, 6, 8, 10, 12, 14, yes, silicon. It won't lose the 4 electrons in this level. What it does to get its stability is it will gain 3 extra electrons, 4 extra electrons. Maybe I should have done nitrogen. So those, I can do nitrogen. Here's nitrogen. Not nitrogen, phosphorus. So there's phosphorus, 2, 4, 6, 8, 10, 12, 14, 15. There's phosphorus. Phosphorus won't lose these 5 electrons to become +5. It will gain extra electrons. If I ask you before I started making this diagram, what's the charge on phosphorus when it's an ion? You would have said -3. It gains 3 electrons. You see what I'm saying? If I had sulfur, there's the electron configuration of sulfur. To get its noble gas configuration, it will gain 2 electrons, and yes, it becomes -2, and so will oxygen. Notice if I go all the way back down here, there's oxygen. So I've just gone up a row. It will gain 2 electrons to become also -2. So you're kind of seeing why these all have the same charge, why these all have the same charge, these all have the same charge, these all have the same charge, these all have the same charge. So noble gas configuration. So really what you're looking at, this pattern, this pattern exists in nature, but this is why the periodic table has the shape it has. Another thing to say is, if I have that configuration, full shell below it, and then one electron in it, I have that same situation. Let me write out the configuration. 1s2, 2s2, 2p6, 3s1, okay, 1s2, 2s2, 2p6, 3s1. All right, and now what if I did this? That configuration, where I have a full shell here, and then I start the S like I did here, this would be 1s2, 2s1. Okay, and let me do, okay, that's that one, but let me keep going. The 4s. Now if I wrote that configuration, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So the outermost electron for these is in an s orbital, and there's only one of them. What I've just done is these three: lithium, sodium, and potassium. What's actually the same in this column is that the outermost orbital is an s orbital with one electron in it. But it turns out these all have similar properties, meaning if they're charged, they'll be charged +1 because they will all lose that one electron. That's one of the reasons they have the same properties. And same for these, they have the same properties because of the electrons. Okay, having said that, so let me do, I was doing phosphorus, 3s2, so I get my phosphorus back. 3p3. So going back to the beginning, there's one way to show the electron configuration of phosphorus. Here's another way to show the electron configuration of phosphorus. Here's one more way to show the electron configuration of phosphorus. We take that. If we took that by itself and I didn't have anything here, what would that be the electron configuration of? The 1s is full, the 2s is full, and the 2p is full. That's the electron configuration of neon. The electron configuration of neon is 1s2, 2s2, 2p6. So, one way to show phosphorus, another way to show phosphorus, and here's one more way to show phosphorus. We go shorthand for 1s2, 2s2, 2p2 would be neon, and then we write these out to the end. So one way to show electron configuration, another way to show electron configuration, and here's a third way to show the electron configuration. You with me? And if you have a periodic table, you can get these in the correct order. You just use the periodic table. But I tell you to go 1, 1, 3, 1, 3, 5, and then remember to sketch one more little 1 in right here in between, and then you get started. And you can kind of see a pattern. Okay, here's another way, and this is the way books like to do it for some reason. Another way. some reason books do it like this. You know, but I think my way is supposed to be boxes. You're going to need more space. Just take that. Books like doing it like this. Boxes. 1, 2. Very similar to this, but to do phosphorus, so there. That's a fourth way to show electron configuration. I think the standardized test probably does something like this. But they're all equivalent. If you understand this, then you understand this. You with me? And yeah, they do stuff like this too. You might see this. 3s, 3p. So now I've got on the board 5 different ways to show the same exact thing. 5 different ways to do electron configurations. You follow all that? Okay. There's one more thing. Called quantum numbers. By the way, the chapter we're in. So went back to chapter 6 for this. Chapter 6.4 does all this. There's even another way to show it. So everything I just described is section 6.4. The quantum numbers and sub S. There we are. Table 6.1. Table 6.1 has the quantum numbers. In N, L, N sub L. These are the 4 quantum numbers. All right, so let me show you those. This is really like kind of another way to show electron configurations. But really, it's like an address system. Quantum mechanical equations are huge, unwieldy things that we won't do much. Maybe we'll do the energy one if we have time. But it's so non-intuitive. I even question whether we should even do it in 1211. But if you have these big unwieldy equations to like find energy or find angular momentum of an electron or stuff, you use these 4 numbers, you plug them into the equation, and you actually calculate with it. So in case you're wondering why these weird numbers, they exist for a reason. To do quantum mechanical calculations. But but I've really kind of already told you this. So I have this. So really the 4 quantum numbers, it's like an address system. It's kind of like an address system for electrons, because we're not going to do the quantum mechanical calculations. So let me put it like this. What if so each one of these electrons has an address. It has 4 numbers that tell you everything about it. So let's say this one. This one is pointing down. So these are like little half arrows, this shape that I'm using for electrons. That's the conventional way to do it. But there's one, in each one of these orbitals, there's one pointing up and one pointing down. Right, but let's say it's this one, and I want to calculate some property out of it. It's angular momentum, it's energy, it's whatever. I need these 4 numbers, okay? And this really isn't hard, it's just not intuitive. The n quantum number is these numbers. So the first shell is 1, the second shell you got 2s, third shell you have 3. And since it's this one I want, the first part of the address is 3. So the n quantum number for this electron is 3. You follow that? It's like if you were writing somebody's address, you start by saying the state, and then the post office knows, okay, this goes to this state. And then you might want to break it down next to the city, right? So to break this down further, those go remind myself of some of the subtle things here. So I've told you what that is. These are all 1s, these are all 2s. The 3s go with 3, that's the n number. All right, the L number, it's telling you which type of orbital it's in. Is it in an S? Is it in a P? Is it in a D? Is it in an F? So we're told we're here in the 3 level. So we're in one of these. The next number tells you which one. The S's, you assign it a value of 0. The P's, you assign it a value of 1. D's, you assign a value of 2. And for F, you call it 3. So this is a handy little translation. So this one that I've highlighted is in an S, so its L number is 0. You with me so far? This isn't complicated, it's just not intuitive. All right. The M sub L number is, you can take each one of these, and if you start in the middle, it's 0. So now I'm deciding, well, put it like this. For the S orbitals, right in the middle here, and for these, let me erase these. I can make this clear. Erase these. Again, I'm taking a long time to explain something that's really not that complicated. Wondering why someone would have this address system for electrons is the only reason it's so complicated. Okay, this is the 1s, the 2s, the 3s. So if it's a S-type orbital, we call it 0. If it's a p-type orbital, we call it as 1. That's a 1. If it's a d-type orbital, it's a 2. So for that one, L is 0. And then the M sub L is this. If you're right in the middle, it's 0. Doesn't matter what type of orbital. If you're right in the middle, it's 0. Over here, this is 1, and this is 2. This is -1, this is -2. This one is 1, this is -1, -1, 1. Okay, so the next letter tells you, are you in the middle, or are you 1 to the right, or 2 to the right, or are you 1 to the left, or 2 to the left? This one is in the middle, so it's 0. M sub S, that means spin. When the arrow is pointing down, we say it's -1/2. If it's pointing up, we call it +1/2. So M sub S, if it's pointing up, the number is +1/2. And if it's pointing down, it's -1/2. And again, the only reason this is complicated is because you're sitting there going, why would you call it 1/2? I mean, who came up with this? It's because these fit into quantum mechanics equations. You would use them for that. So there's the 4 quantum numbers for this electron. It's not really complicated, it just seems convoluted. What about, let's say, we were trying to come up with the address for this electron. So you would start with, it's into 1, this is n equals 2, these are n equals 3, this is 3s, 3p, and 3d, so we're in 3 still. Alright, so that's the first address, we're in 3. The L number, the S is 0s, the P is 1, the D, L equals 2, L equals. So we're in a D-type orbital, so this is 2. Now the M sub L is the left and right designation. So this electron is 0, 1, 2. M sub L is a 2. And I picked one pointing up, so this will be +1/2. There's the 4 quantum numbers for that electron. You see what I'm doing? I know you don't understand why this exists, but that's what quantum numbers are. So you can figure out the quantum numbers. It's not really obvious, but maybe I can make it obvious. There are some combinations that you can't have, but you can have 1, 2, 3, 4. These, in some sense, these are infinite, but you've got level 1, shell 2, shell 3 made up of this, this, and this, shell 4, shell 5. So these can be any integer value. Notice, I usually say L is if you've already designated your n value, like let's say I said the n value is 2, you only get 2 choices. You get 0 up to the n value. So this is 0 and this is 1. So if I said n is 2, then my maximum value of this can be is 2 minus 1, which is 1, and 0. So if I'm in this level, where n equals 2, my only possible values for the L number is 0 and 1. That is, 2 minus 1 is 1. So the possible values are 0 and 1. See, maybe that's obvious, maybe it seems convoluted, but if you're in level number 3, there's only 3 possible values for the L number, and that's 0, 1, and 2, because there's nothing above there. So your L value is going to be between n minus 1, which is 2, and 0. It's either going to be 0, 1, or 2, and that's what this weird equation is trying to tell you. So you can get a question that says, if I'm in level n equals 4, what are the possible values of L? Let me say it like this. If you're in level 4, your possible values are 0, 1, 2, and 3. If you're in level 4, there's 4 of them. If you're in level 10, some ridiculous level way up there, what are your possible values for L? If n equals 10, then it's 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0 are your possible values here. If I continue to build that up, maybe it's obvious, maybe it's not. Possible L values, that is m sub L has to be negative L to L, meaning if I'm in level 3, this is level 3. If I'm in level 3, I'm going to be from, so this is n equals 3, and my possible values here is, and let's say my L was 0, 1, 2. So my L value equals 2. So n equals 3, L equals 2. My possible values are from 2, which is my L number, all the way down to negative 2. So this is saying negative L up to L. Whatever ML is, whatever L is, your possible values for the M sub L is negative L up to positive L. It is kind of obvious looking here, but I know this seems convoluted. But the possible values of M sub L are negative L up to positive L. That's true of all of these. It's just an odd way to put it. And M sub S can always be either plus 1/2 or negative 1/2. So you can get kind of convoluted questions about these. Like if quantum number L equals 3, what are my possible values of M sub L? The possible values are going to be negative 3 all the way up to positive 3. 3. That would be F orbitals. And the 1/2, it can always be up or down, so it can always be positive 1/2 or negative 1/2. So I know they ask questions like that on the standardized exam. I just think this quantum stuff shouldn't be in 1211 because you never do anything with those numbers. It just always seems convoluted. But all about electron configurations and electrons and orbitals. I don't have questions on quantum numbers. I did put up, I started a category for test 3 practice quizzes and electron configurations. So for all my talking today, it's this type stuff. So do look at those and see what you think. I should also say electron configurations, you frequently see it as ground state electron configurations. I don't know if we'll talk about the excited states, but all the electron configurations I talked about today, you'll see them referred to as ground state electron configuration. Okay, what else should I do? guys have it here at the table that I've given you? I'll just give you one. One of the reasons I use this particular periodic table, one thing on there is nice to have. Is that the one I gave you? Draw. See what this book uses. Doesn't come off values. You have enough? I'm tired too. There it is. I will say, four. So we talked a lot about ionic compounds. Do you remember the difference between an ionic compound and a covalent? Yeah, you're on the right track. You get a better pen. So nonmetals, kind of the top right corner of the periodic table, do those become positive or negative when they're charged? These up here, like I said, like if I said, what is the charge on oxygen, what would you say? -2. These become negative. Those are the nonmetals. Everything else, the metals, become positive. They lose electrons. These gain electrons. All right. So if you have oxygen and it's -2, you have magnesium and it's +2. It's sort of like magnesium has lost its 2 electrons, and let's say they landed on the oxygen. Those two become attracted to each other, and you get MgO. That's an ionic compound. So ionic compounds are always between metals and nonmetals. And it's the reason they stick together is what we call ionic bonding. It's literally that charge that's being attracted, and that's why they stick to each other. Covalent is always between only nonmetals. And they don't bond because of charges. Everything's neutral. We did go over Lewis structures. So how many valence electrons is carbon? It's 4. How many for hydrogen? 1. And if you want to make their Lewis structures, you should start going in a circle. 1, 2, 3, 4. So there's a Lewis structure of carbon. And it's a nonmetal. It's a nonmetal. Hydrogen, even though it's on the top left of the periodic table, it's also considered a nonmetal. So I would do that. All right. And let me put a hydrogen up here, and a hydrogen here. And let's do chlorine. What's the valence electrons in chlorine? You count chlorine, but you count to the left, so all the way out to the left of the periodic table.
So there's like 7.
There's 7. And I would go 1, 2, 3, 4. And now I'm coming back around 5, 6, 7. So you would say that chlorine has 3 lone pairs of electrons, and it's got this one single electron. This single electron tells you that chlorine will make 1 covalent bond. These 4 electrons tell you that carbon will make 4 covalent bonds. But let me put the pair down here. I want to put that pair down here. Put this one here. Okay. So now what I'm about to show you is atoms coming together, making a covalent compound. These were covalent compound, ionic compound. And the key is, in the same way when I was doing these orbitals, I would do it like that, and then I would go across and come back. Electrons can pair like this, so you can get electrons to pair from one atom to another. So what you get is, these two can pair, and the way we depict that is we just draw a line. I say there's 2 electrons, and that's a covalent bond. That's what makes these stick together. These do covalent bonding. It's a completely different reason that they're stuck together. It's not ionic, it's the fact that electrons pair. So I finished drawing this molecule. So I'm going to talk about covalent compounds for a while. Also called these are synonyms. A covalent compound is a molecule. But if I went ahead and connected all these together, hydrogen, so I pair those electrons, that's a molecule. You're looking at a molecule. All right. And let me make this a chlorine instead. You can draw a molecule without drawing all the pairs of electrons in there. If you put the electron pairs where they go, you call that a Lewis structure. Otherwise, it's just I guess it's just a structure. But here's what I want to show you. All the atoms in the periodic table have what we call electronegativity. And the electronegativity is so I should say, okay, so there's 2 electrons here. And the point is, they're not really being shared equally. One of these 2 atoms pulls on the electrons a little stronger than the other one. We call that electronegativity. The electronegativity value tells you how strong of a tendency that atom has to pull electrons towards itself. And, I don't make you memorize these, the bottom right corner of these, like for fluorine, you see 4.0. For carbon, you see 2.5. For hydrogen, you see 2.1. Do you see that? So you'll have that on the test and use it for any problem you're trying to work out. But here's the point. What you do to decide which one of these is winning the tug of war of the electrons is you take the absolute value and you go 2.5 minus 2.1, take the absolute value. This ends up being 0.4. And you use these rules. If it's 0.4 or less, we say it's not polar. We say this bond is not polar. But to tell you what polarity is, let's do the fluorine and the carbon. Carbon is 2.5, fluorine is 4.0. Take the absolute value. So what do you get, 1.5? This is the electronegativity difference between carbon and fluorine. You follow me there? Because it's between 0.4 and 1.8, we say that this bond is polar. So what I'm saying is, carbon might pull electrons a little bit towards itself when it's bonded with hydrogen, but it does it so little that it doesn't behave, this molecule won't behave as if those bonds are polar. This bond is very polar. This 4.0 for fluorine compared to carbon tells you that the electrons in this bond are being pulled towards the fluorine by a very high magnitude. Meaning, most of the negative charge in these electrons are pulled over here. If I sort of sketched it, I would say it's kind of like that. The electrons are kind of being pulled towards the fluorine. But what that means is there is a slight, and we do this with a lowercase delta, Greek letter delta. What this is saying is there's not a pull charge like a -1 charge on the fluorine, but there is some charge there, whereas there's no charge here. Meaning if I have let's see, you've got some positive charge here and some negative charge here. And if I had that same thing here, slightly negative there, slightly positive here, you can actually get an attraction between this is CH2F, CH3 molecule. I have this CH3F and this CH3F. If they're together, like they're a gas and they're floating around, there will actually be some attraction from this positive part of this carbon to the negative part of this fluorine. And so that has everything to do with the properties of these. If you're trying to boil it, like you've got a liquid of this, and these are polar, you've got to get it to a much higher temperature than you otherwise would if it was nonpolar, because they stick to each other because of that. So directly related to the properties is this idea of polarity. So you're always able to decide whether something's polar or not. If it was this, there's no polarity for anything to be attracted to. So a bunch of CH4 molecules are not very much attracted to each other, as compared to if there's that polarity there. Follow that? Okay. So if you want to know the polarity of something, you look at the periodic table, you find their electronegativities, you find the difference, and remember it's absolute value. And if it's, you use this as your rule. If it's less than 0.4, there's no polarity in the bond. If it's between 0.4 and 1.8, it's a polar covalent bond. If it's above 1.8, you're probably looking at an ionic compound, meaning the electrons are pretty much all over here. And this one's completely deficient of those electrons. That's when you have, like, MgO. But oxygen has pretty much taken the electrons, and the magnesium has pretty much lost the electrons. So you have an extremely strong ionic bond there. We have to go through the structures. Structure like we're saying. I'm worn out, y'all. I don't think I can do 2.5 hours of class. So I did put some stuff on the polarity up to bond polarity. So look at the molecular shape, look at the bond polarity and the electron configurations and make sure you're okay with them. I think some of the polarity ones, we have to go over, Lewis structures. Some of them I think you can answer. I think it's only question 6 because you're not going to know the structure of these. So you can pretty much do this. So look at those, make sure you're okay with them. And just stop there.